Assalamu alaikum everyone. Welcome back again. As we all know, it's the fifth day of World Space Week 2021, and we have gathered here for our next lecture. The topic of the lecture is stratoscopic platforms, the weather observations, and the speaker for the day is Ms. Maheen Zulfiqar. Maheen Zulfiqar graduated as an electrical engineer from the Institute of Space Technology in the year 2019. Her research interests include signal processing and digital image processing, and currently she's working as a research assistant at Small Satellite Technology and Research Lab, otherwise known as SSTRL Lab, which is under the National Center of GIS and Space Applications, NCGSA. Thank you very much, Ms. Maheen, for being here with us today. You may continue with your lecture.
Everyone can see my screen now?
Yes, Maheen, we can see the screen.
Okay, thank you so much, Sahib, for your introduction. First of all, I welcome you all to World Space Week 2021, and I hope you're enjoying it in a very blessed Friday to all of you. As Sahib has already told you, I have done my electrical engineering from Institute of Space Technology, and I graduated in 2019. Right now, I'm working as a research assistant in SSTRL Lab, which is an affiliated lab of NCGSA. And today we are going to discuss about stratospheric platforms and their role in weather observation. So first of all, we'll start with the brief introduction about our lab, which is Small Satellite Technology and Research Lab, SSTRL. SSTRL is basically an affiliated lab of National Center of GIS and Space Applications, which has 7 other labs also. This is one of their labs. So coming to the missions of this lab, first of all, we are developing CubeSat training equipment, which will be small training equipment for kids, so that they can demonstrate and work on CubeSat. They will be training equipment for them, so they will be used for educational purposes, and these kits are under development right now. Secondly, we are also working on arranging different lectures, workshops, and demonstration in order to instill the knowledge of satellite engineering and satellite in students and in college students and in school students. The main mission of this lab is the development of iCubeN, which is a national CubeSat of Pakistan. This CubeSat will be a 3-unit CubeSat, and its mass will be around 6 kg. And this CubeSat will have all the typical subsystems that the CubeSat carry. So this CubeSat is also under development right now in SSTRL lab. And apart from that, all of the people who are listening to me right now and all of the other universities, they can also participate in the iCubeN development. You can become a focal person in your university and become a part of this iCubeN development. And these are our social media handles. You can follow us and know about the activities we are working on SSTRL lab. You can also become a part of these activities too. So now coming to our topic for today, first of all, I'm going to share the contents with you. First of all, we'll discuss about global weather observation and how the weather is observed globally. Then we'll discuss some of the meteorological satellites, which are basically weather satellites, some of the drawbacks that these satellites have, and why we need a newer system. Then we'll come to the stratospheric platforms, which are now being used for weather observation, and many other applications too. We'll discuss that. We'll discuss these two. Then we'll discuss some high altitude platform communication. How are they communicating with terrestrial system and with satellite system? Then we'll see how these HAPs are used in weather observation and how are they sensing atmosphere. Now coming to the topic, first of all, we need to understand what meteorology is. Meteorology is basically a branch of atmospheric sciences, which basically focus on weather observations and weather forecasting. Meteorology is further divided into two branches or two disciplines, you can say, one of which is observational side and the other is theoretical side. In observational earth science, we basically think and deal with atmosphere and the phenomena that are taking place in the atmosphere. We observe different kinds of temperature changes, moisture changes, humidity, ocean currents, sea surfaces. All of these observations are made under observational earth sciences. And the second branch is theoretical physics. In theoretical physics, we deal with atmosphere as if the atmosphere is a thermodynamical process and it is obeying gas laws. All the ideal gas laws that we study, we apply those laws on atmosphere. So through observational earth science, we gather information and obtain data, and then that obtained data is sampled and modeled through different weather prediction models, and different models are used to forecast weather. So coming to global weather observation, before satellites came to being, this was a very difficult topic, and people were very handicapped because they had very little knowledge about satellite and about atmosphere. So coming to global weather observations, there are basically on a very basic level, there are three systems, we can say there are three platforms that make the whole weather observation system. First of which is a satellite platform, which will be of course in atmosphere. These satellite platforms communicate or send their signals to ground station, which is present on the ground, which is used for communication with the satellite. This is the second platform, and in between these data is collected and processed. After the receiving of information from satellites, this data is processed through different servers and through different AIS data processing units, so they can be used by the user. So coming to satellite platforms, these satellite platforms have sensors, as they are at very high altitude, so they have to have very high resolution of these sensors. Apart from sensors, there are also radars on satellites in order to get distance, angles, and velocity of objects. Radars are basically used to determine the distance and angles of objects. So there are radars present on these satellite platforms in addition to sensors. And satellite has the ability to transmit data directly to ground station through this downlink, which can be seen here. Through this S-band link, satellite transmit their data to ground station, and ground station collect or receive that data through an antenna. So this data is sent directly to ground station, or this can be stored for later transmission. Satellite can store the data and then transmit it later on. So once the data is collected at the ground station, it can be in any form. It can be in image form, it can be in sound form. So the collected data is then transferred to different AIS data processing units. These processing units process the data and sample those data through some prediction models, and then it is transferred to users. As we see weather prediction on our cell phone, so we are basically users in this system. So communication platform consists of a ground station and antenna, through which the satellite communicate with the ground station. So coming to, as I've already told you, that there are different sensors on weather satellites. So now we'll discuss what kind of sensors are present on weather satellites. First of all, there are visible sensors. These sensors have wavelength range of 0.55 micrometer to 0.99 micrometer, and they gather information in the form of images. Essentially, these images are of white and black color. They are black and white images, not colored images. And the regions which appear white, they have more. They are said to be more reflective. So the data that appears, so the image that appears more white That means that the regions it is covering are more reflective regions. As you can see, this is a type of visible sensor. Then there are infrared sensors, which work on infrared band. They detect radiation within wavelength of almost 10.3 to 12.6 micrometer. They detect radiation within this wavelength. They are used to measure temperature of objects remotely. So if an object is present at a remote distance, it can also detect its temperature via these infrared sensors. This is an image of an infrared sensor. Coming to the third type of sensors, which are water vapor sensors. These are also they also detect infrared radiation with their wavelength that they detect is from 6.7 micrometer. They sense the radiation in mid or upper troposphere. So the region in which we live, our immediate atmosphere is consisted of troposphere. So the radiation emitted from troposphere in the form of the water vapors is detected using water vapor sensors which are present in the satellite. Then there are microwave sensors. These sensors detect radiation within a vicinity of almost 1.5 centimeter of wavelength. So the wavelength consists of 1.5 centimeter. These microwave sensors will detect these radiations. And they are very useful because they can distinguish between ground, ice, or snow surfaces. That is very helpful in predicting weather, as they can distinguish whether the obtained image is of ground or ice, or whether if there is snow present. So these are the basic kind of sensors that are present on weather satellites. Apart from them, there are also many different kinds of radar. There is also radiometer present on satellite. So all these sensors that are used on satellite, they have very high spatial resolution. So because they are transmitting from a very high altitude, so they have to have very high resolution. So the images that we get are of high resolution, and we can use that data. So now coming to atmospheric observation, what kind of observations these satellites make in order to predict weather? So they measure sea surfaces. They also if there are any kind of ocean currents occurring in any ocean. They measure atmospheric pressure, precipitation present in the atmosphere. They also measure solar radiation in the atmosphere, critical gas traces, which can be of carbon dioxide or any other critical gases that are present in the atmosphere. They can also observe these gases too. They can also observe wind velocity and wind direction, as direction of wind and velocity is very important in predicting predicting weather and the movement of clouds also. So if you can see this image is actually received in SSTRL lab by our research assistants. If you can see the map of Pakistan, you can see, and this plus sign represents the ground station. IST has its own ground station, so they can actually receive data that the satellites are sending, and they can predict weather forecasting too. So if you can see, there's a lot of white here. So this shows that the region here is cloudy. And if you see here in Pakistan, the region is clear. This image is from 2-3 days back. So in this way, these atmospheric observations are made. These images are received from the satellites, the weather satellites that are orbiting around the Earth. So if you can see, there are also land markings, border markings, markings between oceans and lands too. So now coming to meteorological satellites or weather satellites, there are really two types of meteorological satellites. One of them is polar orbiting satellite. If you see, there are two different types of satellites. One is polar orbiting satellite, and the other is geostationary satellite. The polar orbiting satellites are the satellites that move from north to south. So sorry for this disturbance. So coming back to the meteorological satellite, there are two different types of satellites. One is polar orbiting satellite. These are the satellites that move above or almost nearly to poles. They move from north to south, and they pass over equator at different longitudes. As they move from north to south, if you can see, these are the polar orbiting satellites. They move from north to south. In this way, when they are moving from north to south, the Earth is rotating and or spinning. In this way, whenever they pass, they have a different location. They have a different longitude region for all of their spins. They are comparatively closer to Earth, as they are only 1,000 kilometers away from Earth. So they are comparatively much closer to Earth. They are not very far from Earth as compared to geosatellites, which are very far away from Earth. But the disadvantage of these satellites is that two images cannot be of same location. As I've already told you, when these satellites move from north, has completed its rotation. It has moved one longitude. If you can see the longitude lines, they move when it's moving from north to south. In this time, the Earth has completed its one longitude distance. So in this way, no two images of the same location can be obtained because of the Earth's rotation. So coming to the examples of polar orbiting satellite, there is NOAA, which is National Oceanic and Atmospheric Administration. They have a lot of satellites, which are weather satellites, and they are used frequently. The image that I have just shown you in the previous slide is also received from this NOAA satellite. Apart from that, there is also Indian Remote Sensing (IRS), which are also polar orbiting satellites. There is European Remote Sensing Satellite, which is ERS. All of these are polar orbiting satellites. Now coming to the second type of meteorological satellites, which are geostationary satellites. These satellites are very far from Earth, and you can see they are almost 36,000 kilometers away from Earth. So they are very far away from Earth. They circulate from west. They circle along the equator. So the polar orbiting satellites were moving along the poles of the Earth, whereas geostationary satellites are moving or completing their circle from west to east, and they are moving on the equator. These satellites complete their rotation in 23 hours, 56 minutes, and 4 seconds, approximately in one day. They complete their one rotation around the Earth. But as these satellites are very far from Earth, so they require elaborate telescopes and very high scanning mechanisms. So in order to get high resolution images and so they have very elaborate telescopes and scanning mechanisms. And another drawback of these satellites is that they are very far from Earth, so they can provide information about a fixed point. So in order to completely get information about the Earth, we have to use 3 satellites in order to completely cover the Earth. We need 3 satellites in the orbit. So examples of these geostationary satellites are GEOES West, which is Geostationary Operational Environmental Satellites West, Geostationary Operational Environmental Satellites East, and Indian National Satellite System, INSAT-1. So if you can see, geostationary satellites as well as polar orbiting satellites for weather radars, as they are transmitting information to weather radars, and these polar orbiting satellites are also sending their signals to satellite ground station. And the received data is then sent to some administration or some server where it is modeled and sampled to be used by the users later on. So both of these satellites have same purpose, but they have, but at the same time, it has disadvantages and some disadvantages. Now coming to some drawbacks of weather satellites. In addition to the drawbacks I have told you earlier, there are some other drawbacks. We can discuss them. First of all, these satellites are very expensive to develop, launch, and operate, as they require very elaborate subsystems. So their development process is very lengthy. It takes a lot of time to develop these kind of satellites, and also they are very expensive to launch too, because they require some particular type of rockets to launch these satellites into the orbits. As geostationary satellite is orbiting geostationary orbit, which is very far, so it gets very difficult to launch them in particular orbits and also to operate them. So it's an expensive process. Secondly, ground stations are also very expensive, so they are not available worldwide in very rural areas or very far flung areas or the underdeveloped countries. They don't have access to these ground stations, so it gets difficult to install ground stations too, because their maintenance is also very expensive and requires maintenance, frequent maintenance. Ground stations are also not available all the places. So if there are no ground stations, the weather satellites will not be useful, as they will not be able to send any kind of data to ground stations. So this is one of another drawbacks of these weather satellites. Then they have very limited time span. Though these weather satellites have time span of almost 3 to 7 years, and it can be extended up to 10 years also, but still it is a limited time. After 10 years, they will just be sitting in the atmosphere and just not doing anything. So they have limited time span, and they cannot be received back to Earth. So they will just be creating space debris. They have loss of payload. As I have already told you, once we have launched the satellite, it cannot return back to ground. So all the payload that we have installed on the satellite, which is expensive payload, it is just lost after the satellite has completed its mission, or it has surpassed its lifespan. So it would just be a loss of our resources. And the most important thing is that they create a lot of space junk or space debris in atmosphere, because as you can see, there are a lot of metal and fragments of metal that are just present in the atmosphere. So and it is very dangerous also, and it is very harmful for atmosphere also. So it is creating a lot of space junk, because all the satellites are of metals, and all the rocket launchers that are used to launch these satellites, they are also of metal, so they are just creating space junk in atmosphere. So it is a very important point, and we need to minimize this space junk. Coming to the next drawback, which is sky pollution. Sky pollution and space junk are different. Space junk was mainly concerned with the metal part of the satellite, whereas sky pollution is basically the pollution that is created by the light that the satellites are making. As the satellites gain their receive solar energy, so they are also creating artificial light there. So it is creating a lot of problems for astronomers to study stars, as there is not dark space for them. There is not a lot of dark space for them to study stars and constellations. So it gets very difficult for astronomers. So it is so these satellites are also creating a lot of sky pollution too, in addition to space junk. Now coming to stratospheric platforms. What are stratospheric platforms? So these are basically quasi-stationary platforms that are present in stratosphere, and there are many different names for these platforms, like high altitude platforms, stratostats, stratospheric platforms, high altitude pseudo platforms. So these are the names of stratospheric platforms. They are quasi-stationary. That means that they appear as if they are stationary in stratosphere, and they are positioned in the stratosphere region of our atmosphere. They are all solar powered, remotely operated. All of their operation is done on the ground. Coordinates are set into them, and then they are sent to the on these coordinates. They can be manned or unmanned air vehicles. They are used for wireless communication for rural areas and also metropolitan areas, as stratospheric platforms are used in a lot in 3G services because they are used to expand network. So they are very useful in multimedia communication for rural areas as well as urban areas too. So these platforms fly at an altitude of almost 17 to 22 kilometers, which is also the height of our stratosphere. So they fly at an altitude of 17 to 22 kilometers, as opposed to those satellites, which were nearest satellite was at almost 1,000 kilometers away from Earth. So these are very closer to Earth, almost at an altitude of 17 to 22 kilometers. They have less cost of design and launch, as satellites were very expensive to design and very expensive to launch. These are much easier to launch, and their cost of design is also low. Plus, they are very environmental friendly, as they're not creating any kind of space junk or any kind of pollution in the environment. So these are very environmental friendly also. Very important topic, very important point is as they are complementary systems. They are not a complete answer to terrestrial system, as they cannot completely replace terrestrial system, as well as they cannot completely erase satellite systems. So these are basically a complementary system which will work in addition to satellite and terrestrial systems in order to enhance our communication and in order to give us better and high-speed internet. So this is basically a complementary system in addition to satellite system or terrestrial systems. And the best thing about these stratospheric platforms is that they can be returned to ground, as the satellites were just satellites just remain in the atmosphere, whereas stratospheric platforms can be brought back to ground for their development, for their maintenance also. So in this way, they are also environmental friendly, and in this way, our payloads are also not lost. So these are some points about stratospheric platforms. So now coming to types of stratospheric platforms. There are 3 different types of stratospheric platforms, one of which is lighter than air. If you can see, which are called LTA, lighter than air. They basically contain hydrogen or helium gas, and they contain hydrogen or helium gas bags in them, which help them afloat in stratosphere. Their shape is aerodynamic, which helps them remain in the stratosphere. And some of the examples of these lighter than air stratospheric platforms is Zeppelin and Blimp. Zeppelin is a rigid airship, which is named after a German person who made this platform. And in World War I, it was also used to bomb places, as it is closer to Earth. So it was used to bomb places too. Second example of lighter than air stratospheric platform is Blimp. They are non-rigid, as in comparison to Zeppelin, and basically their shape is maintained with the gas that is filled in them, and also with the envelope that is covering them. Second type of stratospheric platforms are heavier than air. So as these platforms were containing hydrogen or helium gas, they do not contain heavier than air stratospheric platform don't contain any kind of airbags or helium or hydrogen bags. They are made of composite fiber materials like carbon fiber. Examples of heavier than air is Facebook Aquila. Facebook launched its stratospheric platform, which was named Facebook Aquila, and another type is AeroVironment Helios prototype. Facebook Aquila was basically a stratospheric and was basically an atmospheric satellite, and its purpose was to get Earth observation and also to provide internet access. Third type of stratospheric platforms is balloons. They attain altitude of almost 18 to 37 kilometers. So what helps balloons to remain afloat in stratosphere is basically buoyancy, which is a concept I'm sure you all must have heard of it, which is basically tendency of a body to float when it is submerged in a fluid. As balloons have air in them, so the lighter medium would just move upward. So the force will help them remain afloat on stratosphere. So they remain afloat because of buoyancy. Heavier than air were remaining in stratosphere because of their material and their shape, and lighter than air stratospheric platforms were remaining in air because of the hydrogen and helium gas packs present in them. So examples of balloons is blast and weather balloons. Weather balloons are very commonly used. Almost twice a day, weather balloons are released from almost 900 locations worldwide for weather forecasting. So these are the most used system for weather forecasting and weather prediction. If you can see in this image also that these are stratospheric platforms in addition to these geosatellites or LEO satellites. So these satellites are communicating with stratospheric platforms, and these stratospheric platforms are then communicating with the terrestrial system or with airplanes or navigation. So this, as I've told you, these are not complete replacement to these satellite systems. These are just complementary systems as they're connected with satellites through interconnected system. So they get information from satellite and then they increase the area which they can cover and communicate with terrestrial links. So now the question arises, why stratosphere? Why not any other layer of Earth? Why we are only focusing on stratosphere? So troposphere is the region in which we live. So it can be said that our immediate layer in which we live is troposphere. Its altitude is from 0 kilometers to 18 kilometers. And mostly the objects that are found here are mountains, buildings, and most of the commercial airplanes fly in troposphere. Though some of commercial airplanes are now flying in lower stratosphere, but still most of these commercial airplanes are in troposphere. Stratosphere, which is the layer which is used by stratospheric platforms, it starts from 18 kilometers and extend up to 50 kilometers, and the objects that are found here are weather balloons or HAPs. And then comes mesosphere, thermosphere, and exosphere, and they contain meteors, aurora, and satellites. Satellites are the most far away from Earth. So the reason why we are using stratosphere is because they are out of collision range for commercial planes. If we use our stratosphere platforms in troposphere, then it will be very dangerous for commercial airplanes as there is a risk of accidents. So when they are in stratosphere region, they are out of range of commercial airplanes, so the accidents can be stopped. In addition to this, in stratosphere, the wind and turbulence is very mild. So there will be very low turbulence in stratosphere, and the wind is also very mild in stratosphere region. So so that is why we are focusing on stratosphere layer of atmosphere. Plus, it has plenty of sunlight. As I've already told you that these are all solar powered, so they need a lot of sunlight in order for their working. So they need sunlight for this, and stratosphere has plenty of sunlight, so they can easily operate in this region. The relatively uniform and stable wind speed. The wind speeds in stratospheres are also very uniform and stable, which helps in turbulence too. If the speed is uniform, there will be very less turbulence. So that is why we're also using stratosphere. So now coming to stratospheric platforms and their applications. There are many different applications of stratospheric platforms in addition to weather observations, which are navigation, aeronautical, for our commercial airplanes, and for vehicular communications in emergency situations, and also to provide communication or internet access to rural areas. They have a lot of applications. So one of my colleagues has given a lecture on application of these stratospheric platforms, in which she has discussed all of these applications in very detail. I think you should all should listen to that. She has discussed all of these applications in detail. So we'll just focus on weather side of this, weather application of this satellites, these HAPs only. So now, how do these HAPs communicate? As these HAPs have narrowband or broadband services, that means that they can communicate in narrowband, which is small frequency range or within less bandwidth, as well as they can communicate in high bandwidth too, which has large frequency range. They do weather observation through meteorological images, same as weather satellites. They also get, as you can see, this is the ground surveillance area that the HAP is communicating with, and it is sending that images to this control center or the ground station, which has antenna. So basically, its working is almost same as satellites. It gets images and then send it to antenna to ground station. Also, it acts as a relay station. Relay station, what is meant by relay station is that it communicates with satellite, and then it is the middle ground and for terrestrial and satellite systems. So it is in between terrestrial networks and satellite systems. So it is basically a relay station. So they have less development cost and still they have all adequate onboard equipment. They also contain all the sensors that I have told you. They also have radars for the detection of objects. They have all the onboard equipment on them. Now coming to UAVs advantages. Why we are using UAVs for weather? So they have the ability to use meteorological measurements. For example, they can measure wind velocity, direction, magnitude of wind. All of these things can be measured through UAVs. They can also measure low frequency sound waves too. And very important point is that they don't have any risk of losing any expensive sensors. As the sensors I have told you, they are expensive sensors. So if we use those sensors on satellites, they are at risk of losing. But in HAPs, there is no risk of losing those expensive sensors because they can be returned to ground and our resources can be used again. Also, they collect data at different altitudes, which leads to precise measurement. As the satellites are moving only at a particular height and particular altitude, but these HAPs can collect data at different altitudes, so which helps them to get the information about different altitudes, which leads to precise measurements, and these precise measurements will help in gathering information and correct information about weather, and correct information can be passed on to ground station. Also, they are commercially efficient because they are not using any payloads, and they are efficient. They are not very expensive to develop and launch, so they are very commercially efficient. And also, they can be safely returned to home after their flight, and they have completed their mission. They can be easily returned back to ground. So these are some of the advantages that these UAVs have. So now we'll see what kinds of HAPs are used for weather observation. NASA Pathfinder, Centurion, and Helios. So NASA launched its environmental research aircraft and sensor technology, ERAST, which its basic goal was to develop cost-effective and slow-flying UAVs. Under this mission, NASA developed many different kinds of HAPs. First one was Pathfinder. Then with some changes, it was developed into Centurion, and then later into Helios. They were built to serve as atmospheric satellites in order to do in order to get information about weather and also do some research purposes. They can be used for researches around climate. So this is the image of NASA Helios. The project that they started, environmental research, aircraft and sensor technology, terminated in year 2003, but still NASA is working in close affiliation with NOAA in order to develop different atmospheric satellites too. Another satellite that is used for weather observation is Global Hawk. It comes under the category of high altitude long endurance. They can move to a very high altitude and can remain in the atmosphere for a very long time. Global Hawk is basically a surveillance UAV, which is used by military for surveillance. But now it is equipped with weather sensors and lightning sensors too. And NASA and NOAA are both working on this Global Hawk in order to track storms in Pacific Ocean, so they can get information about any kind of storm that can occur in Pacific Ocean, and they can send alerts if there is any community living nearby, so they can alert them too. So Global Hawk is now used for weather observation. Sunglider, it is very new. It flew in the atmosphere for almost 20 hours and 16 minutes. It completed its flight in 20 hours and 16 minutes, out of which 5 hours and 38 minutes were in stratosphere. When this Sunglider was sent to the atmosphere, the conditions were very harsh, almost minus 73 degrees Celsius, and the wind speed was also very high. Still, it received a lot of valuable information for weather. It has remote sensing and observational capabilities. So it made many different observations around the atmosphere of Earth and then came back to Earth. Another type of HAP for weather observation is hydrone. This hydrone is also used for weather observation. This is also very new. This was used by a balloon. A balloon was used to lift it off the ground, and the balloon took it to a height of almost 30 kilometers. The temperature was also very harsh there, almost minus 60 degrees Celsius. The drone also researched around climate change, and it also measured some turbulence in the stratosphere region, and then it came back to Earth in 4 hours controlled descent. It came back to Earth. If you can see, the weather monitoring satellites are almost at a height of almost 22,300 miles, whereas Hedron was released with the help of balloon at the altitude of almost 22 miles. After completing its flight, the Hedron came back to Earth in autonomous way in 4 hours, and it was safely returned to ground. So now I'm going to show you a video regarding Hedron that I've just told you. In this video, you will see how the Hedron was taken to atmosphere and how it made different observations and then returned safely to the ground. And in addition to weather observation, it also gathered information about some ice crystals over Mexico. So these are some references from which this information is taken. Now, if you have any questions.
Thank you so much, Maheen. Do you have, if anyone has any questions, they can raise their hand. If anyone has any questions, they can put their questions in the chat. Okay, since we do not have any questions, I would like to ask all the participants to please turn on their cameras for the group photo. Yes, Mr. Saqib, what's your question? Everyone is requested to please turn on their cameras. Thank you so much, thank you so much, Ms. Maheen, for being here with us today. And thank you so much to all the participants. Have a very good day.